So, yesterday we looked at support vector machines and the kernel trick, where the idea was that your data is not linearly separable as it is currently presented. So, the data is a bunch of vectors in some space, right. So, what you do is that you figure out some way to project it into some higher dimension where it becomes linearly separable, right. And so, in that dimension you find your separator which can be used to classify the data, right. And then this whole thing could be packaged into so called kernel function, which is thought of as a similarity measure, right, which basically does that job for you. And then once you have this, the solution to SVM is essentially a linear combination of these vectors using the kernel function, right. So, now that was about taking the data and mapping it to some higher dimension, and then we briefly discussed about taking high dimensional data and mapping it to lower dimension, right. So, here is one of the reasons why we want to do that. So, the first thing is that most data, like any images or even documents, right. So, when you sort of try to represent them, you get something which is very high dimensional, right. So, even a very standard size image like your phone can take an image which will have these many pixels, right, several megapixels. So, if you try to run any ML algorithm or anything on a large data set of such things, it is going to be very slow. So, that is one of the main motivations. Second motivation is that things in higher dimensions are very different from what we think from, like how we would think about it in lower dimensions, right. So, 2D is something we all understand, 3D is something we all understand, but if you go to some this sort of a high dimension, then distance between two random points is very large. Most of the points, like if you randomly sample a point, I think it's a very high probability that it will basically lie at the, like if you randomly sample a point from the unit sphere, for example, it will very high probability that it will lie close to the surface or on the surface essentially. So, all these things basically make it difficult to maybe understand what the data is or how we should sort of process the data and so on and so forth. Plus, we do not actually need this much information about any object to do most of the ML stuff that we want to do, right. So, the idea is that we take this data which is very high dimensional and reduce its dimensionality to a smaller number, right. So, here is an example. Here you can see that this data is in 3D, right, but essentially data is basically distributed in a circle here. So, there is no need for this data to be 3D. So, you map it down to some 2D plane and then think of that as a circular data in 2D, right. After that, maybe you apply support vector machines. So, once again you project it in 3D, but this time things are very different from how they were initially presented, right. So, the idea essentially is that we want to get rid of all these extra dimensions which we do not really need. So, the way it is done commonly is via this thing called this singular value decomposition, right. So, the idea is that you have some matrix which is a rectangular matrix, right, and because we are in machine learning, we are going to interpret so let us say this is the matrix, right. So, we are going to interpret each row as some feature, right, and each column is some data item, right. So, that is our interpretation of the. So, given some data where each item in the data has some feature, so we stack them, we put them next to each other as column vectors to get a matrix, right. So, our goal would be to reduce the number of rows of this matrix to some smaller number essentially, right. So, that way our data will become low dimensional, right. So, we use this we use this property that any matrix can be decomposed like this, okay, as a product of 3 matrices, where this D is a diagonal matrix. U and V are 2 orthonormal matrices. Essentially, they are composed of unit vectors, and any 2 unit vectors in say U are orthogonal to each other, right. So, the dimension of U is going to be n times k. So, you have so your original matrix was n times D. Now, this time it becomes n times k, and so this K is essentially the rank of this matrix. So whatever you get here, the decomposition, the size of these matrices, they will come out to be basically they will depend on the rank of this matrix, right. So we interpret this matrix U and V, essentially the matrix V, as in some sense a bunch of new abstract features, okay. And if you write this down, in terms of like if you expand out this product essentially, then another way to write this is sort of like this, right. So this matrix M can be written as a linear combination of a bunch of rank 1 matrices, right. So this is another useful way of looking at this thing, right. So this singular value decomposition for any matrix can be found. There are several algorithms for it. So once again I will not go into those algorithms, but what we will try to do is see how this is, we will just try to see how it is used to reduce the dimension, right. So as I said, we have we interpret that these vectors little v, which make up this matrix big V. So interpret it as a collection of new abstract features, right. So what we do is that we take the original data points, right, and once we have one of these V, we will project all those data points along this V, right. And so that this projection, so what is happening essentially, it is like a basis change, right. So when you do a basis change, you write down the old vectors in terms of the new basis vectors, right, and that thing is essentially what, it is just the dot product of the new basis vector along with that whatever vector you had, right. So that is what is being represented here, right. So if we have this as our data point, right, this AI, like this is the ith vector in our data set, then what we are trying to do is to find some vector along which we will project this, right. So this is for one vector, but we actually have multiple vectors, right. So these singular vectors that we find in singular value decomposition, so the first vector that we find, let me just go there. So the very first singular vector that we find, that would be the vector which maximizes this product, right. So here this, you can think of this as what is it, so like the sum of the length, like for every vector take the projection of that vector along V and look at the length of that projection, right, and add up all those lengths, for example, right. So I select the first vector that maximizes the sum of those projections, right. So I thought we had a diagram here, where is that? So if you look at say these 2-dimensional vectors, the blue things are your data points. So you can choose multiple vectors initially as your first singular this thing, but actually the one you will choose, right, would be the one which maximizes the sum of projections along this, right. So you would, the first singular vector will be the vector in this direction, right. The second one would be after you exclude whatever is accounted for by the first singular vector. So the rest, so once you look at all other vectors which are orthogonal to the first singular vector, so take the vector which is orthogonal to V1 and also among those maximizes this, and then the third singular vector will be all those that are orthogonal to V1 and V2 and then maximizes this, right. So this is how, I mean, this is what the singular vectors that you do in SVD, this is the property that they have, and in fact you can actually turn this into an algorithm by just repeated multiplication. So there are many ways of doing this, but this is the key property that we essentially use, right. This is why this is what we use. Yeah, so this is basically the formula for a general like r plus 1th singular vector, right. So you look at only those vectors which are orthogonal to all this, and then among those select that vector which maximizes this. So this keeps happening until essentially you have like the rank of the remaining matrix becomes 0, right. So, you essentially expressed all the vectors in M in terms of these vectors. So, at this point when it becomes 0, you stop, and naturally that comes out to be the rank of the original data matrix, right, and these are your right singular vectors, right. So, this is not so interesting. Yeah, so this is once again expressing the singular value decomposition. So, the way we use this is to come up with the best rank k approximation of a given matrix. Okay. So, let us say your matrix M, the data matrix had rank R. So, then singular value decomposition will give you matrices with rank R, right, and these singular values you will also get that they are sort of in a decreasing order. Right. So, what we do is that we is there an issue? So, as I was saying, right, you can look at this decomposition of M in as something like this, right. You write it in terms of a sum of rank 1 matrices, right. So, if you want the best rank 1 approximation of M, then what you do is that you just take the summation up to only the first term, right. So, here the so when you take it when you take the summation only up to the first term, that means you are looking at the first singular vector, right, and you terminate your summation only there. So, that will give you the best rank 1 approximation to this matrix M. If you want the best rank 5 approximation, then you take this sum for the first 5 terms, right, and so on. So, this is how you come up with some best rank k approximation of a given data matrix, right. So, essentially if you assume that you have data which is of very high dimension, so the original rank of the matrix could be very high, right, because I mean if you look at any real world data, like you have taken a photograph which is a very high dimensional vector, right. Now, even if you and I take the photograph of the same object, the two vectors that we will get are most likely to be slightly different from each other, right. So, in some sense because of the noise in the camera sensor, this and that, like no two vectors are going to be the same, right. So, this matrix M essentially is likely to have very high rank, although most of that rank is made up of noise, right. So, then what you would do is you would do singular value decomposition of this large data matrix, and then assuming some things about the matrix. So, maybe you keep the first 50 like matrices, no. So, you keep the first like you take the summation of that SVD decomposition only up to the first 50 terms, right, for the first largest these singular vectors, and that would give you the best rank 50 approximation of this, and turns out that will actually be very good. So, for whatever reason, I had an example here which is not mentioned, but let me show you. See, so here is for example, so let us say this was a photograph that you have taken, right. So, this time what we are doing is trying to compress an image, right. So, my data is not a collection of photographs, but rather just one photograph, which I think of as a matrix, right, because this is a black and white image, it is a simple matrix made up of like real numbers or something, right. So, I take this matrix, I take its singular value decomposition, right. So, if I take the sum of, let us say this is the original, if I take the sum of first 15 singular values, right, that summation, the first 15 thing, so then I get this. If I take the first 10, I get this. If I take the first 5, I get this. So, I just you can see that as the number of, as you take better and longer summation of that singular value expression, you get better and better approximation to the original image. But even then, see, you can see that this is sort of a good approximation, or maybe this is sort of a good approximation, right. And here this was actually showing n equals 20. For any typical image, actually this rank would have been much higher, right. So, this is a what maybe a 350, let us say 350 by 350 size image, right. So, number of pixels is pretty high here. So, the rank of this is going to be at least close to say 300, right, because there are 300 rows. And what you are seeing here is the SVD summation only up to say first 20 singular values. As you can see that itself is like good enough. If you did not know that, I mean, this looks as good as an original image, for example. Right. So, there are many other examples you can find on the web. See, let us see. So, okay, this one did not open. I was just, so this is a good picture, but somehow this has, okay, great. So, this is another example. So, there was some image, you can even say that this is the best approximation to that image, and this is, well, actually not the original image, but the summation up to 264 largest 264 singular values, right. And as you keep decreasing these things, as in the quality slightly reduces, but even here at 200 or even at say 52, there is not much of a decrease in quality, right. The reason is that most of the information that is lost beyond this point was mostly just noise in the photograph that you had taken, right. So, instead of storing some image which would have been very large like this, you just store this. That is more or less sufficient for most purposes, right. So, here I mean this is just used for image compression, but this is also used, as I said, in machine learning. When you have very high dimensional data, you compress it down to a reasonable dimension which makes sense. So, you should not be choosing something like this, because then this is a terrible, like a lot of useful information is lost, but maybe you choose something based on your previous knowledge that maybe this much is sufficient, and you keep this, right, and this is enough to basically do your machine learning from, right. Yeah. So, this is one of the main uses that we have for these methods. What else did we want to say here? And SVD is also one of the ways you can do this so called principal component analysis, right. So, principal component analysis, the idea is essentially the same, which is that you want to change the basis of the data, so that the first vector in that basis change, it corresponds to the direction of the maximum variance along the data, right. So, here I chose my first basis direction to be this, then the variance of the data explained by this direction is this. Now, after I discard this variance, the next choice would be this, which would explain this much of the variance, and then I mean okay. So, you keep going ahead and do something more. So, I mean this is just 2D. So, for 3D you will have more and more things. So, at some point what will happen is that most of the variance of the data will be explained by some first 50 principal directions in the data, and the remaining explains something of the variance, but that is mostly just noise, right. So, I mean as you basically keep increasing the length of that summation, eventually the what remains unexplained, that much just becomes smaller and smaller. That is what happens. So, once again the stopping point, or how far, like what rank do you use here where you stop, that is something you have to look at the data and figure out, but the idea is essentially the same, right. And in fact, yeah, okay. So, we did not want to do this. So, all I wanted to say was that this is a very common method to first take any higher dimensional data, you reduce it to a much lower dimensional data which is easier to work with, and so on and so forth. And because you do that, a lot of noise is also eliminated and things like that, which also helps improving your ML algorithm, right. So, these are very standard method in mathematics, which I guess most of you are familiar with, but they are basically some fundamental things that people use in machine learning, right. Without this, a lot of things will not work so well. Okay. So, any questions about all these things, like how we use them or something like that? So, once again, if you are familiar with these packages called scikit-learn or anything else, they have all these things built in. And then nowadays, you do not have to write the code for doing SVD or PCA or anything like that. Right. So, there are some very simple standard way of using them, and they will do this for you. Right. So, the only thing you have to keep in mind is that what is it that you are doing, what is the objective of applying SVD or PCA, what is it going to do to your data. So, this is what it is going to do to the data. It is going to reduce the dimensionality of the data, and the way that it does is that it first finds the direction along which most, like the maximum amount of variance in the data can be explained, discarding that the second best direction along which the variance in data can be explained, and so on. Right. And after a certain point, you do not need to explain the variance in the data, because rest of it is just largely noise. So, this is why you do PCA up to a certain, like you look at this thing up to a certain rank, and that is all you need. Right. So, mathematically there are many other connections and interpretation of various things in various places, but I mean that is not needed here at this point. Right. Just the basic thing that what it does here, that is all that we need for machine learning. 53. So, any questions about any of these things? Okay, I mean, I guess it is.
Here K is order of that matrix or singular value.
Here K is some rank up to which you want to approximate the data. Okay, I mean, so your matrix has lot of rows, as I said, right. So, you want to decrease the number of rows by only choosing a subset of these guys. That is all. And the subset that you choose depends on the nature of data you have, right. Like for those images, if you choose some very small number, then that is not a good approximation to the image, but otherwise if you choose a sufficiently large number, that is enough. Right. Yeah, I wanted to do a slightly different topic, which is sort of linear algebraic in nature, but it is not linear algebra. Right. So, one of the things we saw like in the past few lectures was that you can, so we started by building of a linear classifier, right. And what was the linear classifier doing? It was essentially you had some data. So, let me just draw a diagram here. You had some data, and then okay, so we assume the data is linearly separable. We found something like this. In case the data is not linearly separable, you can still do some things and maybe find something that is approximately as good, right. So, maybe this is still a sort of a decent classifier. It does not correctly classify everybody, but it does something up to a certain point. Now, the idea is this. So, while it is easy to build such linear classifiers, right, building maybe some more complex classifier is a more challenging task. Right. So, this idea of boosting, what it does is that it takes a bunch of so called weak classifiers. So, things like this, a linear classifier for data which is not actually linear, things like this. It combines these things. Right. So, it uses multiple weak classifiers and combines them into a strong classifier. So, here the definition of a weak classifier is something very limited, as in it's a weak classifier is any classifier whose error rate is just strictly less than half. Right. So, I mean if you are randomly guessing, your error rate would be half. So, anything which is just better than random guessing can be called as a weak classifier, and we can use a bunch of such weak classifiers to build a strong classifier, which would have error rate much better than this. Right. So, let us see how that is sort of done. Right. So, we have some training data D on which we are building our classifiers. Right. So, what we are going to do is that we are going to associate some weights with each data point in our training data set. Right. So, the weight is sort of going to indicate how much. So, initially when so initially all the weights are, let us say 1, right, all weights are equal. But then after that I build some classifier which I will call M1, right. Now, M1 will correctly classify some things and incorrectly classify some things. So, things that are incorrectly classified, I am going to increase their weights to indicate that the next classifier I am going to build should pay more attention to be correct on these data points, right. So, in some sense M2 that we want to build should try to correct the mistakes that were made by M1, that is what it is. And to make M2 focus on those mistake points of M1, we increase the weights of those guys, right. So, therefore, from the initial state where all weights were 1, now we have another state where the weights of each of the data points have become slightly different. Some weights have gone up. So, now with this new weighted data set I built M2. So, M2 also gets some points right and some points wrong, right. So, then what we are going to do is that we are going to build M3 which will try to correct the mistakes that were made by both M1 and M2 essentially, right. So, to do that once again we are going to change the weights of the points that were wrongly classified by each of these guys, right. And so on until we are sort of happy with the error rate of whatever we have finally obtained, right. So, what is happening is that because each classifier is a weak classifier, which is to say it is slightly better than random guessing. So, each time you build one more classifier, it does slightly better, with all its friends before it, right. So, gradually like the performance of all these weak classifier add up and they become a strong classifier as a group. And each model that I build in this sequence, it also gets some weight alpha I, which is sort of proportional to its error on its training data set, right, on its weighted training data set. And my final output classifier is simply a linear combination of the original classifiers. So, this is, as I want to point out, this is not linear algebra because I guess the object that you have here, this is not a linear algebraic object, it is some function essentially, right. But a linear combination of these weak classifier leads you to a strong classifier if you do it properly. So, here is the algorithm, here is an algorithm called AdaBoost, right. It is it is a very important and I guess like a very surprising to some extent algorithm. So, initially everything has weight as I said 1, but just because you do not want things to blow up, you set the weights to be 1 over n, okay. And then you use some weak classification algorithm, maybe like that linear separator algorithm, to learn some classifier f on the initial data set, right. And this E is the error of this particular classifier, which you just get by running the classifier on all these guys, right. And this error rate also takes the weights into account. So, this is the weighted error rate, but initially all weights are 1. So, it is just normal error rate. After that you see if the error rate is too high, right. So, at this point you basically just stop because there is not much you can do at this beyond this point, right. Otherwise, the classifier is like better than half. So, you define this number beta t to be the error rate divided by 1 minus error rate for whatever reason, and you update the weights by, here I said you will increase the weights where you made mistake, but as I said you do not want to blow up the numbers. So, you decrease the weights of those things that the classifier gets correct, and others you just keep it as it is, right, and then you normalize these weights. So, this is the algorithm. And after you are done, the final classifier is just this, right. So, that alpha I becomes essentially log of 1 over beta, right. So, there is a theorem which proves that all of this what you are doing is correct, which we are not going to go into, but the algorithm itself is very simple. You just keep going through in loop, wherever there is a mistake you increase the weights or you relatively increase the weights of those mistake points, right, and then you build a new classifier under this new weight scheme, right. And the effect that this has is that everything, like a linear combination of all these things, seems to take care of most of the errors. Right. So, in fact, this is a very general thing, as in each of those models that you build, it could be a very different type of model. Right. So, you could use linear classifiers, you could use some other clustering, some this, some that, but even you can use anything you want. Right. And still you can just sort of combine all these classifiers and get a stronger classifier. So, let me actually ask you a quick question. Right. So, here as I said, the final classifier out of adder boost is a linear combination of the initial classifiers. Right. So, and I also said that we can use like the linear separator, that perceptron algorithm, for example, as one of our weak classification algorithm. Right. So, what was the output of the perceptron algorithm? Positive or negative, right? So, as in there was a hyperplane that was learned by the perceptron algorithm, and then if your input point is over here, then maybe it will give you -1, and if it was over there, then it will give you +1. Right. So, the input to perceptron algorithm is a vector which represents your data point, and the output is +1 or -1. So, notice something. So, while the classification itself is based on some hyperplane and linear algebraic notions, the perceptron, if you think of it as a function where the input is something, the output is something, that function is not a linear function. Right. Input is some vector, output is +-1. That is not a linear function. Right. For example, linear functions. Okay, why is it not a linear function? Can anyone tell me?
Final set first of all. The range of the linear operator must be a subspace, but ±1 is not a subspace.
0 to 0. 0 to 0 is bias.
0 to 0 is also.
But the most simple reason is simply that a linear operator, so it distributes over its summation of inputs, right?
Yes.
So that is not going to happen in Fourier. If you add a vector twice, you will cross that domain. So that is one of the other reasons. But okay, so my point is that perceptron algorithm gives you a classifier which is built around this linear hyperplane separator between things, but the function itself is not a linear function. What happens if you have a classifier which is actually a linear function? For example, you are doing regression. Input is something, the output is also a vector or a number or something. Do you think you can use, for example, a linear regression class function over here?
Probability of being 1 or
No, that is logistic regression. I am saying, suppose your perceptron, for example, is not a linear function, but suppose you had some other classifier which is a linear function. Then do you think you can use it in this adder boost as your weak classifier or a weak learner?
After all, it is given to give you either plus or minus 1, and based on that only the errors will.
No, so plus or minus 1 it gives you because it's a it's a classification algorithm, right? But you can also have these regression problems where the prediction, as I said, is a number or a vector or something. So a regression can also be done by essentially some linear function, for example. So then unlike the perceptron, that object itself will become, the whole thing is a linear thing. Input is linear, output is also linear. So it is a linear operator essentially from the input. So do you think I can use linear operators in this?
Technically, we don't see, at least I don't see any problem in using it.
Anybody else?
As it is give some real number, as it's you can take average, and if it is value above the average, you can get it +1 or -1. And
No, I'm not about +1 -1. That is not okay. Maybe I'm confusing you. So let me explain what is happening. So what is this here? What is my final classifier? This is a linear combination of my base classifier, the weak. But if this itself is a linear function, and you take a linear combination of linear functions, what do you get?
Yes, on the linear.
Exactly. So, if your weak classifier was a linear function, the final output classifier of this boosting, this adder boost algorithm is also a linear function. If linear classifiers were a weak learner, why would that be a strong learner? Because you have not moved out of, you were, like, you could have directly found a weak class, like a good classifier here, right, if it were possible. It is a weak classifier only because your model is so weak that it cannot actually do this. So, if this weak classifier is actually a linear classifier or a linear function essentially, then it's not going to, you cannot boost it. It has to be a non-linear thing. And then a combination, a linear combination of non-linear things can actually be stronger than the original thing, right. So, that is one of the key things here. I am just trying to see if, so here is a example, maybe I should have led with this. So, let us say this is your data set, right, which a priori does not seem to be linearly separable, for example. So, the perceptron algorithm will not really do a good job, it will not terminate, but maybe you can run a variant of the perceptron algorithm that does the best that it can, like SVM for example, or something like that. You just try to find some linear separator. In fact, let us not even say you find a hyperplane, but maybe try to find a horizontal or vertical line that does the best classification, right. That is even weaker. It is some sort of, like, just look at one of the values of these vectors and just say which side it should fall into. But that is going to be a non-linear thing, because you will take some vector and you will output a plus minus 1. So, the function is not going to be linear, it is going to be a very simple non-linear function, right. So, I maybe learned this, I figure out that maybe this line is one of these classifiers that I can find here, right. Everything to the left of this line is positive, everything to the right is negative, and of course, this line is not, it is a very weak learner, as in it will get these three things wrong. So, in the next step I need to, what I will do is that I will increase the relative weights of these points as compared to the other points, because they were wrongly classified by this thing. And I am going to learn a new classifier which gets this new data set with the weights correct, as in I will measure the error as a weighted sum, right. So, this classifier now qualifies because these guys have really high weights. So, they will push this line from here to there, that is essentially what has happened, right. But when you do that, you get some other things wrong. So, once again you have to adjust the weights of the things that you have gotten wrong and learn a third classifier which is like this, right. So, this time it becomes a horizontal line. So, at the end your final classifier is going to be, as I said, a linear combination of the original, these three classifiers, and you will also get some weights which are based on the error rates of these guys. And pictorially the resultant classifier is something like this, which as you can see is not a linear classifier, right. I mean, it is actually a very complicated classifier. So, this is what boosting does. So, adder boost was the sort of first algorithm on these lines, I think, and then people have figured out better algorithms which maybe converge faster or things like that, like XG boost, gradient boosting, things like that, right. Okay, so any questions about this boosting thing? The key idea was simply that you can just take linear combinations of a bunch of weak learners and get to a strong learner. So, I do not know if I should discuss this. This was, well, it has nothing to do with linear algebra, but let me just add this because it is interesting to know. So, basically for any linear algebraic model there is this thing called bias variance trade off, right. So, I also get so bias essentially means how expressive the model is, right, and variance essentially is like how sensitive your model is to the change in the data values, right. So, if you reduce so if you take some very weak classifiers, they are not going to be very expressive, but also they are not going to be very sensitive to the data variations, which is to say they are not going to overfit, right. So, this boosting method what it does is that it combines a bunch of weak classifiers into a strong classifier. This strong classifier, the bias is lower because it has more expressive power at this point, or I do not know how you call it, but what happens is that the variance, like its capacity to overfit the data also goes up, right, because if I keep building a very, like if I keep computing more and more these things, right. So, in no model is, so what is happening here, right. So, here I was trying to basically change the weights of the data points, so that the new classifier gets the wrong data points correct, right, and this can keep happening over and over again until maybe at some point we fit everything, right. But if you fit everything, that is essentially overfitting, because most data that you get in the real world will have some noise. So, if you try to at some point essentially you are fitting noise that was present in the data rather than the data itself, right. So, you do not want that to happen. Now, some certain models like these sort of very weak classifiers, they simply do not have the capacity to overfit, right. I mean, they do not have that much expressive power in the first place, but something like boosting can combine these things into something that has like very large expressive power, right. So, if you look at this picture that we get here, right. So, this picture essentially means that if I had a sufficiently long sequence of these weak classifiers, essentially I could draw almost any curve in the 2D plane in some sense, right. So, that is a very strong classification power, right. So, almost any kind of data that can be sort of separated into two halves by some kind of curve can possibly be approximated by add a boost using such kind of these things, right. So, this bias variance trade off basically says how strong your model is compared to how likely it is to overfit, right. So, boosting for example, up to a certain point gives you sort of a trade off between how much power your model has versus its capacity to overfit. But the nice thing about this, which I really like, is that I mean it is a linear combination of some objects which are not actually linear algebraic objects, but it gives you a strong classifier, right. Okay. I mean yeah. So, I guess this is not really linear algebra, but yeah, like ideas from linear algebra is sort of used like this, right. So, in the next couple of lectures we will look at some other things which, for example, how neural networks are built. Again, they are built using very simple ideas from linear algebra, but they end up they are very effective in machine learning essentially. So, very simple like things based around dot products or things like that, they somehow seem to work very well, right. So, yeah, machine learning does not really use very sophisticated linear algebra in any way. It uses very simple things. It is just they are used in a very clever manner, right. Like this add a boost algorithm, that perceptron algorithm, they are very simple, but it actually took lots and lots of research to arrive at them in some sense. Because if I initially just give you the perceptron algorithm and do not give you the proof, I mean you will not believe that it will work, right? Why should a linear combination of the data vectors give you a good classifier? Makes no sense. Or why should a linear combination of a bunch of weak classifier give you this strong classifier, right. So, I think these things actually won some, I do not know, Ada Boost should have won some award, no? Let us see. So, he won the Gödel Prize in 2003 for AdaBoost. Right. So, that is one of the highest prizes in computer science. And it is based on some very simple ideas, but yeah.
Which price, sir?
The Gödel Prize. Can you not see the screen? Oh, okay. So, look up AdaBoost on Wikipedia. Not sure why this is not happening. And yeah, look up the authors of that work essentially.
Okay, sir.
Yeah, yeah. Oh, it's also written in the first line. Yeah, 2003 they won the Gödel Prize.
Actually, I cannot zoom, so it's look like hazy, so that's why I cannot read. Okay. Ada boost.
Yes. Okay. So, any questions about all this stuff? So, if there are no questions, we can just stop now.
No, sir. No, I have no question.
And this classifier that we used here, these are called decision stumps. So, all they do is that they look at your data, look at one attribute of the data, and based on the value of that attribute, give it a positive or a negative label. So, this is like possibly the simplest possible classifier you can think of for data, but even that can be combined to a very sophisticated classifier.